So hi everybody, I'm Laura Sommovigo and I am a PhD student in Scuola Normale Superiore in Pisa in Italy, and I work under the supervision of Professor Andrea Ferrara. Today I would like to discuss about worm dust in high redshift galaxies, its origins and implications. So at this point I think it's clear to everybody that thanks to the Atacama Large Millimeter Array, in the last few years it has become possible for the first time to observe the far-infrared emission from higher redshift galaxies, unveiling the presence of dust even in these very early stages of galaxy formation. However, many challenges remain open, and some of the reasons are, in my opinion, well summarized in this plot from the paper by Liang 2019. On the left side, you see the spectral energy distribution of a redshift galaxy, which is well sampled by data points on both sides of the gray body-like spectrum, meaning that from SED fitting, one can easily, so to say, infer the dust temperature, dust mass, obscured fraction of star formation, and far-infrared luminosity of this galaxy. However, for the analog at redshift 6 that you see on the right side, ALMA band 6 and 7 only trace the right side of the spectrum, and in general, very few data points are available, just one or two, meaning that it is very difficult to simultaneously infer the dust temperature and the dust mass of these sources. What is done instead is to generally assume the dust temperature, meaning that all the other derived properties of the galaxy are heavily dependent on this difficultly testable assumption. In this sense, SPICA might help us in the following years. This is a proposed new instrument at ESO, and it will have some mid-infrared windows for these high redshift sources. Let me now move to the theoretical part of the talk. So I'm going to describe the dust temperature within giant molecular clouds through semi-analytical models. So why do we want to focus on giant molecular clouds? This is because from simulations from Pallottini 2019 and Behrens 2018, we see that regions which mainly contribute to the far-infrared emission of high redshift galaxies are indeed giant molecular clouds, which are the yellow dots in these plots that I'm showing. In our model, we consider uniform molecular cloud in terms of density, star forming with a central stellar cluster. We leave as three parameters: the turbulent velocity within the cloud and the pressure within the cloud. Here is my parameter space for the clouds, and in particular, I would like you to focus on these two points. So the blue one should be representative of a Milky Way-like cloud, so a local-like cloud, and its properties are taken from average properties of observed clouds in the local universe. Instead, for the red point, this should be representative of a typical high redshift cloud. In this case, clearly, I don't have any observations to take the properties from, so I get the data for this cloud from simulations. You can see that the high redshift cloud has both larger pressure and larger turbulent velocity, meaning that it survives longer to both supernovae and stellar winds, having a lifetime or dispersal time, which is 4 times longer than the local-like cloud. Let me now move on to describe the dust temperature profiles within our clouds. So in this plot, on the y-axis, you have the dust temperature, whereas on the x-axis, you have the distance with respect to the center of the cloud, where I remind you that we have our UV source. So the red line is our the dust temperature in our high redshift cloud, while the blue line is the dust temperature in our low redshift cloud. You can see that the high redshift cloud has a hotter dust, and this is mainly due to the fact that this cloud has larger pressure. We can understand this in physical terms because we know that the optical depth scales as the mean square root within our semi-analytical model of the pressure, meaning that the distance at which we reach optical depth equal to unity is much closer with respect to the center of the cloud in the high redshift cloud with respect to the local cloud. So in other words, dust is hotter in the high redshift cloud due to the more compact dust configuration in this structure with respect to the local analog. This is the basic setting of our model. We also include the effect of radiation pressure, and we see that these conclusions do not change. And we find dust temperature as large as 60 Kelvin and above within our high redshift cloud, and luminosity to gas mass ratio of around 10 solar luminosities over solar masses, which is 10 times higher than what observed in local clouds, which is also consistent with what we get for our simulated local cloud. This larger dust temperature has some important implications. When I say larger, I refer with respect to what are the current assumptions on dust temperature at high redshift. And here I'm showing you a plot which on the y-axis has the dust mass, and on the x-axis, the age of the galaxy. So the black curve is the dust production model from Asana 2014. And I would like you to focus on these two sets of points, which correspond to the dust mass that Tamura 2019 would need for their observed galaxy, assuming a dust temperature of 40 Kelvin or 50 Kelvin, in order to get the observed far-infrared luminosity of their source. So the point is that if you allow for larger dust temperature, in order to produce the same FIR luminosity, you need less dust mass. In particular, if we consider a slightly larger dust temperature of 60 Kelvin and above, we are perfectly in line with both the Asana model and constraints from supernovae studies, as we only need less than 0.3 solar masses of dust to be produced in each supernovae explosion. And we can allow for some dust destruction during the lifetime of the galaxy. This suggestion is also been met recently by new observation by BACS 2020, which have given a new lower limit for the dust temperature within this galaxy of 80 Kelvin by adding the observed far-infrared flux at 160 micron rest frame. Another implication is related to the IRX-β relation at high redshift. Allowing for larger dust temperature means that we can reduce the tension between local and high redshift IRX-β relation. And this is because allowing for larger dust temperature results in larger far-infrared luminosity, shifting the far-infrared faint data points upwards in the IRX-β plane. However, we have to keep in mind that in our high redshift cloud, the optical depth is very high, meaning that UV is heavily obscured, which is also what was shown in the simulations. So in our scenario, the observable UV radiation should come from stars that have already dispersed the molecular gas around them, so clouds that have already been dispersed. This is in favor of a scenario of spatial segregation between far-infrared emission and UV emission, which should come from spatially separated regions within galaxies. And this is also in line with some recent observations, such as the one by Bowler 2018 and Laporte 2019, which observe a spatial offset between the HST data and the ALMA data, so between the UV emission and the dust continuum emission. This might lead us to question the validity of the IRX-β relation at high redshift, since this relation assumes the co-spatiality of the two emitting regions, so the UV and the far-infrared emitting regions. Finally, I would like to conclude by presenting some preliminary results on a new method that we are developing, which is aimed at constraining the dust temperature using only one continuum observation, which is what we generally have for high redshift galaxy. Here, I'm showing the case of the same galaxy I was discussing before in terms of the dust mass. So the galaxy at redshift 8.31, observed by BACS 2020 and Tamura 2019. For this galaxy, with our method, we get a dust temperature of 83 Kelvin, which is perfectly in line with the lower limit given by BACS 2020. I would like to remind you that BACS's method relies on SCD fitting, so they use 3 continuum data points, whereas we only need one by combining it with the C2 line emission. Nevertheless, you can see that we have very large uncertainties on our predicted dust temperature, and this is mainly due to the fact that the metallicity of these galaxies is largely uncertain, and this enters in our method's computation. However, JWST should help us in this sense, since it is expected to reduce the uncertainty on the metallicity of high redshift galaxies. For instance, if we consider a very reasonable reduction down to 30% of relative uncertainty, we reduce the error on our predicted dust temperature, narrowing the range within which the dust temperature can vary between 80 Kelvin and 120 Kelvin. This method has some relevant applications in the context of recent ALMA large programs such as Alpine and Rebels, which both target C2 emitters at high redshift. I leave you to my summary, and thank you for your attention.
Thank you very much, Laura. Please do post your questions. Let me see. So there is a question from Tom. Have you considered variations in dust model size composition? Thanks.
So you mean different grain sizes, right?
Yeah.
Okay, so yes, if I can show you a backup slide I have. So, okay, so here actually I'm showing the dust temperature profile and the density profile that we get, as also including the radiation pressure effect. So it's slightly different with respect to what we see before. And this is because basically the radiation pressure creates a cavity at the center of the cloud and a very dense shell at the boundary of the H2 region. However, the point I would like to show is the second plot, the one that is getting larger right now. So the color bar shows here different grain sizes, which we consider from 0.01 micron up to 1 micron. And you see that depending on the grain size, we have slightly different dust temperature. So before I was showing also always the case of 0.1 micron, which is a typical grain size. But whenever I'm computing the average dust temperature for the cloud, I'm always averaging on the grain size distribution and either on luminosity or dust mass. So I hope I've answered the question.
So I think you did. So here's another question. Maybe I missed the point, but how are you measuring T-dust in your simulation? And how this would compare to the fit of MBB to your simulated SED? And what about the optical depth? Even at lower redshift 2 to 4, when having 10 points of the SED, TD is not well measured.
So you mean related to the last part, the preliminary result, right?
I'm not entirely sure. I'm just reading the question, but
okay, so I think is related to that. So so basically what we do, I also have a backup slide for this. Okay, so basically what we do is, starting from the usual formula that is used also in SED fitting, we rewrite the dust mass as a function of the dust gas ratio and the C2 to total gas conversion coefficient, so that we get the dust mass is the product of these two quantities and the C2 luminosity. So at this point, by fitting the single observed data point at 1900 gigahertz or 160 micron, we can get a reasonable prediction on the dust temperature and dust mass. I don't know if this answers to the question, but eventually we can enter in more details in the chat if I have misunderstood.
Yeah, I think it's related to the fact that even at lower redshift, we have sampled a lot of the spectra, and fitting the SED to that spectra gives very uncertain results.
Yeah, but indeed you see that also, I'm going to show again our prediction. I mean, you see that our predictions still have very large uncertainties now. So clearly, we can only qualitatively constrain the dust temperature using only one observation, but still, it's better than nothing. And without this method, what one does is to simply assume the dust temperature and proceed to compute all the other properties, such as dust mass and whatever, based on this assumption. So at least we can constrain the region in which one can vary the dust temperature in the initial assumption. Again, I don't know if I answered to the question.
Yeah, so there is another question related to that, so maybe you can answer it again in a chat. But another question was, what percentage of the IR luminosities contributed from warmer dust in your model?
Okay, so actually we have, so this is the, okay, so this is the spectra that we get at the beginning of the lifetime of our two clouds. You can see that while for the local cloud, we have a almost perfect gray body, for the high redshift cloud, we have a slightly modified shape. And this is exactly because of the warmer dust, which mainly contributes to this part where you can clearly see that there's a sort of like double peak situation going on. And indeed, at shorter wavelengths, we have that the warmer dust, so the one at the peak that I was showing before, is contributing the most. However, when we do we also show two different weightings for our dust temperature. So here I'm showing you the dust temperature, luminosity weighted and mass weighted for our simulated clouds. Especially, I would like you to focus always on the red lines, which are the ones related to the high redshift cloud. You can see that if we think of mass weighting, the dust temperature is really low because most of the dust mass is found in equilibrium with the CMB. Whereas if we consider luminosity weighting, so basically we should be considering the gas which is mainly contributing to the emission, we have larger temperatures. So the one that is mainly contributing to the emission is exactly the warm dust. And we have dust temperature of around 60 Kelvin for our high redshift cloud when we include radiation pressure, and much larger when the radiation pressure is not included, which is the case, for instance, also of the simulations where for spatial resolution reasons, one can not include the effect of radiation pressure. I hope I answered.
Okay, thank you, Laura. There are more questions. Apparently, dust is a very hot topic, so you can answer them on the chat, but we need to move on.